Again. Yeah. Now look at that. It's fine. See what the whole looks like. We got to do data. So types of this monitoring.
Let's I didn't quite get a chance to go through evaluating limits for complex fractions. So I know that showed up in your homework. Let me just go through one of these and then see if you guys have any questions. So we're dealing with, sorry, this is page 11. When we're dealing with complex fractions, we never want to assume anything. We just always want to take the first step, which is doing direct substitution. Right? Let's see what's happening here. So if I plug 0 in for x, I'm going to get 0 over 0. So that will confirm that there's a hole in the graph. The order pair doesn't exist, but the limit does. We just have to find where that hole is. The big hint here is we can clearly see what's causing the 0 in the numerator, right? In this case, it's x that's causing that 0. And the denominator is also producing 0, but ultimately we know that there's an x hiding in this portion of the expression that's causing that 0. So the strategy is, if I can find a way to merge these two fractions together, if I can add these two fractions, make it one fraction, then hopefully there will be an x that shows up, and then I can begin to pair and hopefully cancel out. So we want to add the two fractions, but to add fractions, we have to do common denominator. So the common denominator is going to end up being 4 and x minus 4. So if I balance, well, first identify that we do need both the 4 and the x minus 4 to create a common denominator. And then we want to balance each fraction. So this x minus 4 is missing a 4 from the full denominator. So I need to multiply the top by 4, and then that will give me a balanced fraction that is equivalent to 1 over x minus 4, but with my new common denominator. And then with my second fraction, the 4 has been transformed to a 4 and x minus 4, so it's missing an x minus 4. So I need to balance the numerator with an x minus 4. So then 1 times x minus 4 is x minus 4. Now that I have common denominator, I can merge them into the same fraction by adding my numerators together. So 4 plus x minus 4 gives me just x over 4 times x minus 4. So it doesn't look like we made a whole lot of progress, but if we were to replace this with the new merged fraction, then we're able to move forward, get closer in terms of finding something that actually cancels out. So if I took the two separate fractions and merged it into my new common denominator fraction, I now have x divided by this fraction, x over 4 times x minus 4. Now, something divided by a denominator is same thing as something multiplied by the reciprocal of the denominator, right? So x times the reciprocal of this becomes x times 4, x minus 4 divided by x. And now I can clearly see, okay, I can see a pairing and a canceling out of what's causing the hole, remove the hole, and then reevaluate. So when we reevaluate, we're now hoping that we can get into something other than 0 over 0. In this case, 4 times 0 minus 4 is negative 16, or 4 times negative 4 is negative 16. So we basically have 3 main categories with evaluating limits algebraically. The first is if we get 0 over 0, is it something that we can cancel out by factoring and reducing? If it's involving radicals, and typically we want to be multiplying top and bottom by the conjugate. And then if there's a complex fraction, typically it's going to be common denominator and then multiplied by the reciprocal and then canceling out the whole and then reevaluating. But for all these problems, we never want to skip the first step, which is testing to see what's happening there. We always want to do direct substitution as our first step, even though you feel like you know where the problem is headed. Okay, so never skip that first step. On the AP exam, they're looking for confirmation before you jump into your other steps. So I'm going to remind this to us as we get closer to the AP exam next year, but they do have some issues with equaling 0 over 0. There's a whole debate in terms of, is it really equal to 0 over 0? And so on the AP exam, they're really picky about equal signs, meaning that when you put an equal sign on the AP exam, on the free response question, they're looking very carefully on both sides of the equal sign and seeing if they're actually equal to each other. But the way that we use equal sign a lot of times is we're not really committing to the fact that they're equal. We're just saying that this is the next step. But the way AP exam is graded, the graders are instructed to look at both sides of the equal sign and actually confirm that they're equal. If they're not, they may take a point off. So the way you get around it is you use arrows. If you use arrows, then they can't take a point off, but you're just telling the grader, hey, I'm just showing you what my next step is, but I'm not saying that these are equal to each other. And this really comes up as an issue with limits. So I would say with limit problems, use arrows, and then that way you won't lose any points. I'm not going to take off any points if you use equals or arrows, but just letting you know what the AP graders are looking for and that they're picky with equal signs and arrows. So if you ever use the equal sign in AP exam, make sure that both sides of your equal sign are actually equal to each other. So that's just something that I will point that out to us as we get closer to the AP exam as well. All right, let's move on. We'll see about it. May want to highlight a few more problems before we get to today's topic. Okay, this is a bit of a strange one. This is number 16 on page 12. We're trying to find the limit as x approaches 2 from the left side of 2. One way is you can graph it, but it feels like this is kind of hard thing to graph. So here's one way that we can think of it and also this is good practice for how to handle absolute value functions. So let's just step to the side and just look at what we're dealing with the absolute value of x minus 2. So I'm going to step off to the side and just talk about that absolute value of x minus 2, just the numerator portion of this problem. Now, any absolute value function we can rewrite as a piecewise function because absolute value function feels a little bit cumbersome in terms of working with it. But we know that ultimately absolute value of x minus 2 is really this, right? It's really just a V-shaped graph with a vertex at 2, 0. Okay. And we can think of this as a merging of two linear graphs, one with a positive slope, the other with a negative slope, and with the two graphs with a certain ending and starting point. So we can think of absolute value of x minus 2 then as x minus 2. This represents the portion of the graph with a positive slope. But we only want to show this positive slope graph to the right of 2. And there's also a negative slope version of the graph, of the linear graph, which is a negative parentheses x minus 2. And this one is showing to the left of 2. This point is defined, so you can choose either to put the line underneath, either the top or the bottom. It doesn't matter. It's just not both of them. So I'm just going to pick the top one, but either one is fine. Now, we know that this is not the full expression, right? This is only the numerator portion, absolute value of x minus 2. But if we know that this is the same thing as this, then we can divide everything by x minus 2 and see what happens with this piecewise function. So the function that we're really worried about is absolute value of x minus 2 divided by x minus 2. So if I can divide this by x minus 2, I can also divide both these by x minus 2. Now, let's see what happens when we do that. What happens if I do x minus 2 divided by x minus 2? This goes to 1. What happens if I do negative x minus 2 divided by x minus 2? Negative 1. Now, this feels difficult to graph, but this is a lot easier to graph, right? We can graph this without any issues. That's just two horizontal lines. So this one is y equals 1, but we only want y equals 1 to the right of 2. I'm going to have the point defined here. And then there's a negative 1 to the left of 2. Y equals negative 1 to the left of 2. So this is the graph. And now we can just look at the graph and evaluate the limit as x approaches 2 from the left side of 2. So I'm going to pick a point to the left of 2. I'm going to head towards 2. That y value is holding steady at what? Negative 1. So that's my one-sided limit. Writing absolute value as piecewise linear functions will come in handy later on, but I think that's a good skill to review. It's just a note about your homework. I want to see all your work, even your AP practice. I know there are some problems where you really can't show much work, but majority of the problems you should be able to show your work. So keep in mind that I've worked out all the problems on my website. So if you go to the limits page, if you go to the date that the homework is assigned, you should be able to see links to both the textbook problems that I worked out and to the AP practice. So if you're stuck on the steps, try it first, but then look to see if the solution key can kind of help you move along. And obviously, if you're having trouble with everything, then come to the help session. I'll have help sessions every morning, 7:45. Some students have been coming in just asking 1 or 2 questions, which is fine. That's great. Even if you just need help with 1 or 2 questions, I think it's good to get those questions answered so it doesn't build up to the end of the unit and you just feel overwhelmed, right? So any small questions that you have, I want you to ask. Some students have also done this in the past, and I don't mind if you do this. Some students, they're stuck at home and they're stuck and the solution is not helping them. Sometimes students will take a picture of the problem that they're stuck on, and they will send me a text remind. And if I have time, I'm able to, eventually I'll get to it and work out the problem and send the steps back to you, especially if you feel like the steps that I've provided and the key is not sufficient. So I really want to make myself available. Either help session in the morning or you can text me if you have any questions. Send me a reminder. I may not be able to get to it immediately, but I typically respond pretty quickly. I want you guys to feel like you're getting supported with every, because we're going to move fast, and sometimes I'm not able to go through every little thing that would normally go through with AB students just because of the pace that we're going through. So, but yeah, definitely reach out if you're having any questions about anything. All right. Okay, let's go to page 18. Okay, here's the idea that we have to be able to, we're going to be using limit notation to help us prove if a function is continuous or discontinuous. And there's different types of discontinuity we're going to talk about. So a continuous function is simply, can you sketch the graph without having to lift up your pencil? If you can, then a function is continuous. So here, this graph, this polynomial is a continuous function. There are no holes, there's no asymptotes, there's no sudden breaks in the graph. We can sketch the graph without ever having to lift up the pencil halfway through our graph. This, however, is a discontinuous function because there's an asymptote. So in order to move to the next part of the graph, I have to lift my pencil up to sketch the other part. So anytime you got to lift up a pencil, basically if there's a hole, an asymptote, disconnected branches, we have this continuous function. So we have different types of discontinuity. If there's a hole in the graph, that means we're only 1 point away from achieving continuity at that point. So we call that a removable discontinuity. If we have a discontinuity due to a vertical asymptote, where we have two completely separate branches of graph, we call that non-removable discontinuity. Now, if I have separate branches of the graph where the graph is maybe a segment and then it's going to pick up at a different point and then it becomes a curve, this is also a non-removable discontinuity. This is not because of a vertical asymptote. We just call this a jump discontinuity. But it also falls under the category of non-removable. Okay, for each function, identify the type of each discontinuity and where it is located. So if I can factor everything out, I can look for discontinuity. Basically, whatever is left in the denominator will be a vertical asymptote. Basically, anything between numerator and denominator that cancels out will be a hole in the graph. So if I factor my numerator denominator trinomial factoring there, multiplies to be 12 and adds it to be -8, -2 and -6, multiplies to be -10, adds it to be 3, x minus 2 and x plus 5. So we know there's a hole at x equals 2. There's a what at -5? Yeah. Now, this x minus 6 is not a discontinuity, but it is something that is a feature on the graph. Do you know what this x minus 6 tells us about the graph? Good. It's the x-intercept. Yeah. So it's not discontinuity. I just want to kind of make sure that we see all the different parts and understand all the different parts of a rational function. Number 2. Numerator, I can't do anything with. Denominators, difference of squares. I can break it down into x squared plus 1, x squared minus 1. I can't go any further with x squared plus 1, but we can continue with x squared minus 1. That's also a difference of squares. So we can clearly see hole at x equals -1, vertical asymptote at x equals 1. There's leftover x squared plus 1, but if I try to set that equal to 0, I'll get an imaginary number. So there's no real number that can come out of this. So there's no discontinuity here. So as a general rule, if we're looking at a rational function, discontinuities will come from the denominator of a rational function. A leftover denominator that doesn't cancel out is vertical asymptote. Any denominator that cancels out with a numerator, it will be a hole in the graph. So here's the formal definition of continuity. We can tell by looking at the graph whether a function is continuous at a point, because if we see any sort of a break, it's obvious it's not continuous. But in order to prove continuity, we are going to use limit notation to prove whether a graph is continuous at a point. Okay, whenever we prove continuity, it's only at a point. We're not talking about the entire graph. We're just zeroing in on one point and trying to decide is the graph connected at that point, or whether there's a break. So go ahead and spend a minute to write this down, and I will go through each part with you. So the first condition is whenever you're asked to prove if a function is continuous, you're always going to be given information in terms of where the target is. You're never going to have to guess where, at what point we're trying to find the continuity for. There's always going to be context clues in the problem where it's going to be pretty obvious what the C value is. So we never have to guess what the C value is. You're going to usually be, they're going to be told where the center of this problem is. So the first thing is the point defined? Okay. Obviously, if the point is not defined, then we know the function is not continuous. So it's the point defined. So let's say at C, the point is defined. If it is, then we can move on to the next step. Even if the point is not defined, we're going to continue with the second condition, because we're going to have to, we know it's already not continuous, but we're going to have to be able to determine the different types of discontinuity. And we can't determine the type of discontinuity with just the first condition alone. We're going to move on to the second one. Okay, so let's say the point exists, so it passes the first condition. The second condition would be, does the limit exist, right? So limit is talking about the approach. Is the graph approaching the same y value from both sides of the target? Again, the point doesn't have to exist for the limit as long as the graph is connected towards or moving towards a point. So let's say the graph looked like this. Would this pass the second condition? Yes, right. If I pick points on either side of C, and if I drew arrows towards C, they're both pointing me to that hole. They're both pointing me to the same y value. So this is the notation that indicates what we talked about the arrows, right? If I pick 2 points on both sides and I can draw the arrows, and the arrows are moving towards approaching the same y value, then the limit exists. Sometimes we can get away with just one limit statement. Other times we have to write out the one-sided limit and actually go through that process. And I will talk about when we can rely on just one statement and when we have to take additional steps with one-sided limit statements. Okay, but either way, first condition passes with this graph, second condition passes. Now the third condition is asking, is the approach the same as the order pair? For this one, we would say what? No, right? We see that the limit is headed towards some y value, but the order pair is living at a different y value. This point is not the same as the limit, so it would fail the third condition. This one would be discontinuous. This one would fall under removable discontinuity. Now, if the hole was getting filled in by the point, then all three conditions would pass, and then the function will be continuous with all three conditions passing. Okay. Let me show another instance of a graph not continuous. Okay. Let's say the graph looked like this, right? We have a point that's defined, and then we move on to the second condition. Does the limit exist? And let's say the graph looked like this. would this pass the second condition? It would not, right? This would fail because if I pick point to the left of C, it's taking me to a different Y value than if I pick a point to the right of C and move towards C. We can definitely tell it would fail the second condition. Then we would say that there's this discontinuity because it's a non-removable discontinuity. If it passes all three conditions, my function is continuous. If it fails the second condition, we say it's a non-removable discontinuity. If it passes the second one and fails the third one, we would say it's going to be a removable discontinuity. We only look at the third condition if it passes the second condition. Okay? If it fails the second one, we already know the limit doesn't exist. There's no need to look at the third condition. All right, let's look at example 1 here. This is where we're going to prove continuity with the conditions that we've established. Let me write those out again. Okay, so state whether the function x squared minus 2x plus 1 is a parabola that's to the left of -1, and there's a linear graph that's between -1 and 2, and there's 2 to the x that's to the right of 2. We just want to know, at these junctures, are the graphs actually connected? And if they're not connected, then we have to use the conditions to help us decide, is it jump discontinuity, is it hole discontinuity? Okay. And then we're told what the C value is. So for A is at x equals -1. Okay, so first things first, let's find what our order pair is. If the order pair exists, we're just going to do f of -1. And then based off the conditions, we want to see where is -1 defined. Is it with the first, second, or third piecewise? Second one, right? There, x is greater than or equal to -1. That is with the second condition. So just plug -1 in for x. What do we get? 1. Okay, so we know the order pair exists. We're gathering data. Second condition. Does the limit exist at x equals -1? So the issue here is that we see there are two different graphs on either side of -1. We're not going to be able to rely on one limit statement. We're going to have to rely on one side of the limit. We need to basically do a approach from both sides separately and then see if those approaches are headed towards the same y value. So we're going to do the limit as x approaches -1 from the left side of -1. So which expression is to the left of -1? First one. Okay, so I'm going to write that out. X squared minus 2x plus 1. Okay, I'll evaluate that in a second. Let me write out the other side. Limit as x approaches -1 from the right side of -1. This one will be where? Second one, x plus 2. Now, the negative and the positive notations is just to tell you which piecewise we're working with, but we're just going to plug in the integer value that we see. So -1 there for x, I'll get 1 plus 2 plus 1, which is 4. If I plug -1 here, what do we get? 1. Does the limit exist? No, right? 1 is headed towards 1. 1's going to 4. This is obviously jump discontinuity. So then we know what type of discontinuity it is. We know the function is not continuous. So we can say the limit as x approaches -1 of f of x does not exist because we don't want to say 1 doesn't equal to 4. We want to say because the one-side limits are not in agreement. This is the way that you would write it. Limit as x approaches -1 from the left of f of x does not equal to the limit as x approaches -1. Sorry, -1 from the right side of 1 f of x. This is the justification that we're looking for. And because of this, we can say, therefore, limit doesn't exist. And it doesn't specify to identify what type of discontinuity, but just for practice purposes, we're going to say this is a non-removable discontinuity at x equals -1. All right, part B. Now we have a different C value. Now we're just focusing on x equals 2. And we're going to just go through our conditions, find the point, see if the limit exists. And then the third condition is just looking back at your first two conditions and seeing if they're in agreement. So if you reach the third condition, you're never creating a new set of data. You're just looking back at your first two and comparing. Okay? So there's no new data to collect for 3. The third condition is just looking back at the first two. All right, go ahead and try part B. I'll work the same time that you guys are working through it and see if we match. And pay attention to your notations, just like how we did with part A. First condition, I'm looking at my restrictions to see which function to plug into. If I want to find f2 is defined for the third piecewise. So 2 to the second power is 4. We can move forward. Second condition, we see that the graph is split on either side of 2. There's a different graph living to the left of 2 as there is, compared to the graph to the right of 2. So we need to find the limit from both sides of 2. So from the left side of 2, we're going to choose the x plus 2. From the right side of 2, we're going to choose 2 to the x. And the one side limits, they're both producing the same y value. So we're going to make a conclusion that because these are the same, we can conclude that the full limit is equal to 4. And if my order pair, and now the third condition is looking back at the first two and seeing if we have agreement. F of 2 equals 4, limit is 4. So they're both in agreement. Now, for the third condition, I see some students, they would just say 4 equals 4, and therefore the function is continuous. I want you to be to write it out this way. You don't have to involve the number 4 in your third statement. You're just going to write out the statement as you see here. You're going to say f of 4, basically replace your c with the value that that we're centered on, and just keep it all keep everything else the same. So really, you're just writing the third statement, replacing the c value with a number, and then let that be your statement to represent the third condition. And obviously, all 3 conditions pass. We can say the function is continuous. Now, we're only committing to the fact that the function is continuous at x equals 2. We don't want to just say the function is continuous because we don't know what's happening anywhere else. We just know that at that point, the function is continuous. So we want to specify that we only tested continuity at x equals 2. Okay, let's go to page 19. So sometimes we have problems that feels more complicated because there's like a missing variable. But my strategy is anytime I see the word continuity, I'm just going to blindly follow my continuity conditions. And the nice thing about doing that is if you follow your conditions as set, it gives you a structure to follow. And before you know it, you're going to be able to solve for whatever you're looking for just by following the conditions. So let's look at number 3. I want to show you an example where just following the conditions, we can get to the answer without having to try anything else except to follow the conditions. So number 3 says, let the function be defined by f of x equals x squared minus 3x minus 18 all over x minus 6, where x does not equal to 6, but then the y value is a whenever x equals to 6. Okay. Now, what is this x doesn't equal to 6? What does that mean about this expression? Where is this function defined? Everywhere except 6. Okay, so I wanted to make a note of that. I know it's obvious for many of us. I just want to just point that out. Everywhere except 6. Okay. Now, we can write this a different way. You're never going to see it written this way, but I think it helps at least to kind of visually see it at least one time. This is kind of a overkill in terms of writing it this way or writing a different way. So we say that this is everywhere except 6, right? So that means to the left of 6, we're talking about this graph. To the right of 6 is also this graph. And this is just a what? That's just a, okay, point. It's just a point, right? We're just defining an ordered pair here, but the connected parts of graph is with the first piecewise. So I'm just going to do this once because we're not going to write it out this way ever. But in case, I think it helps just to kind of see what this really means. So this is really a shorthand way of writing this one, right? And the reason that we don't write it this way is because it feels like overkill to write the same expression that's to the left of 6 and to the right of 6. But that's basically what's happening, right? Everywhere except 6 means to the left of 6 and to the right of 6. The graph is the same on either side of 6. It's just defined differently at that point at 6. Right, it's asking for what value of a is the function continuous at x equals 6. Let's just step through our continuity conditions, and before we know it, we're going to solve for a without even trying to. So what's our c value? Just 6, right? So we're just finding f of 6. So f of 6 is equal to what? Just a, right? We don't know what a is, but we're just gathering information. This is as far as we can tell from what we were given. So we can move on. Second statement is, does the limit exist? We can do one-sided limit, but are we going to get anything different if we do one-sided limit? It's the same, right? It's the same function. If we do a one-sided limit, we're going to get the same result. So the idea is that if you're getting an x that's equal to 6, then there's no need to do one-sided limit. You can, but we only want to really do one-sided limit if we're seeing that we have different functions defined on either side of 6. And here, it's clear that's the same function on either side of 6. We're just going to rely on one limit statement. Now, if you see a less than and greater than with different functions defined, then you definitely want to use one-sided limit. But here we can skip it since we're only dealing with the same graph. Okay, so this goes back to algebraic evaluation of limits. What's the first step that we take? direct substitution, right? Let's just see what was happening. What happens if I plug 6 in? 0 over 0. We know there's a hole, right? So we keep going. We know there's a limit waiting for us at the end of the problem. There's a real number. Factor. Multiplies to be negative 18, adds it to be negative 3. Okay, what happens? Yep. Reevaluate, and we get what? We get 9. Okay. We keep going, right? Third condition. What will it take for my function to be continuous? I need what? I need these to be the same. F of 6 must be equal to 9, so A must be equal to 9. And if we just step through our conditions, we can solve for whatever we're looking for without having to try for it, right? We just step through conditions and our answer will just naturally show up. Okay, let's try that strategy for number 5. Again, this is the same function defined on either side of 5. There's no need to do one-side limit. We can just find order pair, evaluate the limits, and then we can solve for A. Our C value is 5. F of 5 is A. That's defined with the second piecewise, which is just the point. Limits. We're talking about the approach, but know that we're talking about the same graph on either side of 5. There's no need for one-side limit. Jump directly to just that first piecewise. Always do direct substitution first. We get 0 over 0. We know there's a hole. Factor, cancel out, reevaluate. The limit exists at 8. So in order for the first two conditions to equal each other, I need f of 5 equal to 8, which means that A is equal to 8. Okay, tomorrow we're going to talk about squeeze theorem, intermediate value theorem, and if we have time, we can start with infinite limits. But there's homework tonight. Again, help session 7:45 in the morning if you need any help. All right, go get your phones.